Okay, welcome back. We'll continue our lecture. We'll do chapter 5. Chapter 5 is we are going to look at another subsystem available in satellite, attitude control system, ACS. I think previous lecture, what we have seen the propulsion system, and we have also discussed that the propulsion system can be used not only to do a translation motion from one spot to another spot, but also rotational motion to have attitude motion in a spacecraft. So this particular chapter 5 is going to look at specifically how are you going to have uh, rotational motion in a spacecraft so that you can practically point towards to, for example, planet Earth without even having your rigid body tilted left or right, or rather, north or south. So those kind of rotational motions, you have it in the spacecraft or in the satellite, and we have a specific rotational motion controller, which normally we say attitude control system, that is going to help us to basically to ensure that we are not actually rotating in our spot. So when you start actually rotating, imagine if you start rotating all those three axes, so practically you're going to lose your pointing towards the planet Earth. So we will see that, and specifically we are going to see how are we going to induce a rotational motion in a particular satellite or in a spacecraft. Okay, let me divide the satellite into two major components. We have done, I think, a lot of subsystems. Technically speaking, if you look at any satellite, it'll be two major parts. The mission itself on top is practically its mission. It could be a radar mission, it could be a telecommunication mission, it could be an Earth observation mission, it could be a scientific mission. So this is quite mission driven, I would say. The payloads, you can call this payloads. The payloads are basically mission driven, and a particular payload is going to be very, very unique for a particular mission. So if you have a telecommunication mission, then you can imagine that you have transponders, antenna, that's a payload. But on the other hand, if you look at it, practically this is a platform, a satellite. If you look at it, it means that all those missions that you have in mind, let's say Earth observation or even a radar mission, we can actually embark those payloads onto a particular satellite, in fact, satellite platform. So all your subsystems that actually we have been discussing throughout this semester are practically inside this platform. So when we later I will show you how this platform, when I cut open this platform, what are the equipments inside. So that those equipments inside should also reflect to all those subsystems that you have been actually covering in satellite technology. So therefore, when you look at a satellite, there is two major components that always you can see, two major parts in fact. The payload, which is a mission-driven component or part, and you have that platform or satellite, which consists of all those subsystems which enables the satellite to fly and to maintain its orbit while during the mission. So therefore, you can have a particular platform, and you can keep on selling the platform for a different mission or different client. So if you ask me, if you want to be a satellite engineer, the good idea is basically to be a platform engineer rather than a particular mission expert, or rather a particular, well, I would say a payload engineer. For example, let's say you're going to probably work on a radar, so you have to actually look at missions that that is going to actually take a payload which is a radar. Then you are relevant. But regardless of what payload, if you are working as a satellite engineer, the platform engineer practically, then like it or not, you need to fly the satellite. Therefore, you are actually needed in all times when you want to actually fly the satellite. So focusing, that is the reason. If you look at it, our satellite technology is focusing more on the payloads rather more on the platform rather than the payload, in fact. All right, let's go on. Now, how to we have seen how propulsion system is helping satellite basically to move from one spot to another spot. And now, when I'm basically in my orbit, I'm rotating or orientating myself towards the planet Earth. I don't want to have a rotational motion in the rigid body, because when I have a rotational motion, practically I can't point my antenna towards the planet Earth. So therefore, the rotational motion, which is the attitude motion, we need to control it. So we need to have certain actuators. So in this case, practically, we have actuators within the satellite that can help us to stabilize the attitude. That means to nullify that rotational motion. So it's basically when you are rotated, let's say towards my left, let's say you're rotating, then I need to actually correct back by rotating otherwise, yeah, on my right side. So then I can be stable. So there are basically you can rotational motion in a satellite can be induced, or rather can be obtained by these four means, as you can see. Now the stabilization, this is a spin stabilized technique, which is going to help us also to stabilize. What exactly happens? The whole satellite, assume this is a satellite, the whole satellite is going to actually spin. So it is just like a top spinning. You play a top spin, so it's just like the whole rigid body is spinning. When you have the whole rigid body spinning, obviously you will induce a gyroscopic stiffness. Therefore, the rotational motion are actually helping to stabilize the satellite. That is one way of stabilizing the satellite. This is quite a primitive way. In fact, Nyasat 1 is being stabilized using spin stabilization. That means you can imagine that it cannot be a cubical rigid body. It has to be a good cylinder, a symmetric cylinder, better still, and you spin the whole body. The antenna will be looking at planet Earth, for example. The whole body is spinning. So this can be also done by spinning and stabilizing the whole satellite. So now this is not a very good idea, in fact. Well, it looks simple, but imagine you are spinning up the whole body. Now, if you spin up the whole body, assume that actually you have solar panels. The solar panels also will be actually quite in a difficult situation, basically, to face the sun. So it may not be a good idea to spin the whole satellite. Maybe what we should do is that we should probably spin a particular part or component within the satellite to induce that gyroscopic stiffness. That means I have an angular momentum, or I can have a torque when there is something actually spinning within the satellite or rigid body. So the idea of a momentum wheel came by to replace the spinning action. How is that? You have a wheel, simply it's a wheel, a rotor, which spins fast. So when you spin fast, basically you have an angular momentum, and this angular momentum is going to help us to stabilize this particular satellite. So the concept is very similar, but only thing is that here you don't rotate the whole body. You only rotate a particular wheel, so to say. Okay, it's a momentum wheel, call it. Then we are actually embarking this maybe in a one axis. Assume that you want the stabilization in all the three axes. You can imagine that I should be having three different wheels in all those X, Y, Z axes. This is what is actually shown here. This is particularly a three-axis stabilized satellite. It can be we call it a reaction wheel, where we embark into all those three axes. Now, importantly, I have drawn here basically a cylindric satellite. But when you talk about only requirement for a spin stabilization satellite, preferably it is a cylindric, I would say, volume. But other than that, all these satellites can look very much different than the cylindric, I would say, option that we have. This could be a cubical satellite. It's fine, absolutely no problem. You can still embark the wheels inside. And likewise, the reaction wheel, when you have a cubical satellite, you look at modern satellites, most of the satellites are cubical, in fact. If you look at, for example, satellites that we fly today, very seldom actually you will pick a cylindric, well, I would say satellite in that sense. More often than not, it will be more like a cubical satellite. So therefore, if you want to stabilize the satellite, all three axes want to be stabilized, you can use an option of a wheel stabilization, which is a reaction wheel. Another one, quite similar to momentum wheel. Assume that you are spinning the rotor very fast. Now, if in this option, in momentum wheel option, basically the momentum wheel is basically installed in one particular axis, and it is spinning. But can you imagine if you can move the momentum wheel? That means there is a mechanism which can allow the momentum, the spinning momentum wheel to be tilted. When you start actually doing that, technically speaking, I can do a stabilization not only in the spinning axis but also in the tilted axis. So you can imagine, if you have 3 axes, if I could tilt it, I should be able to also stabilize not only one axis but also the other axis. So that is the concept. So you can imagine it can be tilted. Now, more importantly, again, this could very well be a cubical satellite, not necessarily have to be a spherical satellite. Okay, so how to induce rotational motion for stabilization in a satellite? One of the good options that we have is basically by having a rotor, a spinning rotor. Okay. Now, so let me combine these two options that we had last time. We were exposed to propulsion system. We call them thrusters in the satellite, and we have also a momentum wheels or even a reaction wheel for stabilization. I bring all this and I start installing in the satellite. What I have here, I have 3 axes. I need to be stabilizing 3 axes. I can have 3 reaction wheels. Done. So I can induce a rotational motion in all those 3 axes, X, Y, and Z. On top of it, and this is called an attitude motion. When you have a rotational motion, it's an attitude motion. But when you have a translation motion, it is more often than not, it's an orbital motion. So in order for me to have a translation motion, I can have a thruster systems here, which you have been exposed to, which is going to help me to move the satellite up or down. And when I operate the reaction wheel, it is not going to actually have a translation motion. It is going to just have a rotational motion at this particular point only. But when you want to move the satellite into a different orbit, for example, from one spot to another spot, you must have thrusters. So as you can see, there are 2 good actuators that have been presented here, or rather in the 2 different chapters that we have seen, and we have brought them and to see how they have been installed in the satellite. Again, thrusters can be used to control the orbit because it gives you the translation motion. Reaction wheels can be used to stabilize the attitude of the satellite because it gives us the rotational motion. But other than these fundamental motions and actuators, we have also other varieties of I would say actuators that we can actually pick and choose to induce rotational motion. Okay. Now, on my left side, basically, if you can see, all these are sensors. Okay, all these are sensors. Now, in order for you to fly in a particular orbit, you need to have sensors sensing the motion of the satellite. It could be the position of the satellite, it could be the rotational or attitude of the satellite. Attitude means the rotational motion of the satellite. So in order for you to have that, you should be sensing it. So a typical sensor we have called sun sensor. As you can see, if I say sun sensor, it says what? It is maybe it's going to sense sun. Yes, indeed. It is a sensor which actually look at the sun and it knows exactly where is the direction. So cause sun sensor will tell you basically where exactly is the direction. Cause sun sensor typically is like a photocells, okay? But you have fine sun sensor which also focuses on sun and tells you the exact line, the line of sight. It tells you, well, this is where I'm looking at sun. So you are supposed to be actually looking at sun here. So I know my planet Earth is at the back. So, and unfortunately, sun sensors can only work in the sun phase. When you go to eclipse phase, you don't have the sun, you can't be actually depending on it. You have magnetometers. Now, magnetometers, I think you have been exposed to magnetometers in your lab. Magnetometers is going to help us to measure the magnetic field strength, the Earth magnetic field strength. So once we measure the Earth magnetic field strength, we can technically tell not only the position but also the attitude of the particular satellite. We can know that. Okay, there is some calculations that we have to do in order for us to determine that. Then we have gyro, fiber optic gyro initial reference unit. Just like in aircraft, we do have gyroscope. Gyroscope measures the angular rate. that is going to also give us the information of the rotational motion of this rigid body, whether the rigid body is looking at planet Earth or it is already been rotating. Yeah, and that can be done. Then for positioning, we have a GPS, global system, receivers, that will give you the exact position where you are exactly in that particular orbit. That can be done as well. So technically speaking, you have here, you have the attitude sensors and you have the orbit sensors. GPS is going to give us the orbit information, sun sensor, magnetometers, and the fiber optic gyro is going to give us the rotational motion. So you have a complete set. On the right side, if you see, all these are my actuators. Now, as we have looked into thrusters, as you can see, thrusters are going to help us to induce translation motion. Okay, you have hydrogen thrusters. Well, there's also an option of electrothermal hydrogen thrusters also. So there are different sorts of thrusters, but in a nutshell, thrusters are going to induce that rotational motion, the translational motion primarily, but it can also help you to do a rotational motion if you want. But more often than not, we will pick the typical wheel, the reaction wheel or momentum wheel, to have the rotational motion. Now, more importantly, as you can see, from Earth magnetic field, I can measure the Earth magnetic field, then I can practically deduce my attitude. How to do that? There is a calculation that you can practically learn in spacecraft dynamics control, your elective subject. But not only the magnetic field is helping us in order for us to get some information of our attitude, but also it can actually help us in order to induce a torque. Now, for example, this reaction wheel, when the reaction wheel spins, you have basically the velocity, which is the angular velocity. When you have angular velocity, you have a mass, then you should be having that angular momentum. When the angular momentum changes, you should be able to have a torque. So when you have a torque, which it is going to help us to induce a rotational motion. So as you can see, if the body is facing rotated to this direction, I want to now look at towards to this back to this direction. I need to actually rotate the body this way. So what I need torque. So that can be actually very well done by having the wheels. There is also another actuator that can give you the rotational motion, is the magnetotorcus. It is a simple, you can imagine, you have an Earth magnetic field, then you have, let's say, a electromagnet. Let's say you on this particular electromagnet, so you will have two magnets, the Earth magnetic field, and you have the dipoles of your magnet. So both are going to actually react because they have fields. So when they react, technically speaking, you should be able to induce the torque. And of course, there are formulation how to induce the torque. You're exposed to subjects like in subjects like spacecraft dynamics control. So this is a actuator, gives us the torque. It's also called torcus because it gives us torque. Wheel is also going to give us torque. So rotational motion is taken care, and the thrusters is going to take care of that exact translation motion. All this can be put into a onboard management unit. So the onboard management unit is nothing but a computer which has, for example, a choice of actuators and sensors, acquisition, safe hold. What are the choices that actually you can have? So you can see acquisition, safe mode, you can use a minimum sensor, okay, and actuator. Normal mode. Normal mode is where you do your mission, business as usual, normal mission. So choices of selections of actuators and sensors are also given. Now this is just an example. Deboost mode is going to actually, you can imagine when you say the deboost, that means you are, technically speaking, you are going to maybe do a translation of motion. So therefore, you can imagine when the thrusters are on, more often than not, you are doing a translation motion. Okay? Now you can't, so 24 hours, the rotational motion has to be taken care. Translation motion, not every time. Because remember, thrusters need fuel. You can't simply on every time, you will actually lose fuel. So even in orbit, if you look at the orbit control, we don't do orbit control every day. So there is a periodic orbit control. You need it, you on the engine. That means you on the thruster. If you don't need it, you switch it off. That's how it's been designed. Okay, go on. Now remember, I promised that I'm going to cut open the platform. Okay, can you again go back to the first slide, please? Yep, here. What I told you just now, I'm going to cut this open. I'm going to cut this platform open, and let's see what is inside there. This is what you see inside. All these subsystems basically you have been exposed to. Only one thing is pending still. Onboard management unit, onboard OBMU, onboard management unit is just like the computer, which actually manages all these actually subsystems. So you can see we have been exposed to thermal, we have been exposed to power system, battery, photovoltaic cells, antennas. Yes, we will cover in upcoming chapters. Momentum wheel, we have done. Talkers, thrusters, position, basically GPS, and this is basically the bus that you use. Bus is technically, this is example of 1553. B basically is just that protocols of communication. That means how you are going to actually lay this particular protocol, typical protocols for arrangement of the equipment. So there are standard ways of doing it, so that everybody, let's say you buy an equipment from a particular manufacturer, there's already a standard. So the same equipment can be basically embarked to your satellite without any problem, because we communicate in the same manner, so to say. That means the protocols is the same. So it's just an example, right? So this is what is needed for you to fly the satellite. This is exactly what you need to have to fly the satellite. So this is exactly that what you have been exposed to in satellite technology. So this goes inside the platform, and you can fly the satellite even without the mission. So this is the minimum that you need to have to fly any satellite or rigid body in space. Go on. Now the last slide basically is going to give me a bit of information on orbit and attitude sensors, since we talked about it already. For example, sun sensor, it is going to measure the direction. Here I'm just going to give you the accuracy. That means how accurate the sun sensor is going to be. It can give you up to 0.005 degrees. That's very, very fine pointing. Okay. Now, nothing is free. When the pointing goes higher, the cost of the equipment is going to go higher as well. Star sensor speaks itself. That means you are going to actually look at the formation of stars. Those days, you can see in all these seafarers, they've been using stars to navigate. So likewise, why not satellite can use that as well? So there's an equipment called a star sensor, basically to help us to find the actual pointing. That means the attitude. Earth sensor, well, when you can actually look at the sun, why not we can also look at planet Earth? So when you fly planet Earth, when you look in front and on your side, you can see horizon actually. When you look down, you can't, because why? You can only see the land or the surface of the planet Earth. But if you can see, if you fly, if you look at front, that means the flight direction, you can see the horizon. Likewise, left and right. Okay, so therefore, when we want to actually navigate, we can also use Earth horizon, and all these are basically attitude sensors. Attitude sensors. Magnetometers is another attitude sensor, but the problem with magnetometers is that the accuracy is very weak. Okay, it's very weak. Can go up to about 3 degrees. Then comes the very common and commonly used attitude sensor, gyroscope. Gyroscope is fantastic. It's one of those very, very important equipment or sensor that they use in satellite in order to get your actual attitude reading, just like in your aircraft as well. So these are the options that we have, and all this I've given you. Technically speaking, this is actually going to give us attitude, okay, attitude sensor. Now for orbit, specifically you can derive even with magnetometers also, but it's not going to be very accurate. So typically this is what you have, and I've also given the power budget, etc., and of course how heavy it is going to be. Yeah. All right. Thank you.